Hello and welcome to lecture 1-3, which is all about oxidation numbers and redox reactions. So we're going to do as usual, make sure please that you have already completed your learning targets in your learning target notebook. If you have the good foundation here, then we're going to add some examples and we'll clarify a few things that might have been challenging for you. So stop the video if you need to, and when you're ready, restart it. Okay, here goes. So you have some rules that you wrote in your learning targets about determining oxidation numbers. So remember that an oxidation number is the charge that the atom would have, a single atom. This is a really important distinction here. This is a charge that a single atom would have in a molecule or within an ionic compound if the electrons were completely transferred. So we're not talking about the total positive or negative value of that. We're talking about the value according to one atom of that type. And this is an important distinction. We'll talk through this as we're doing a few examples. I know that in molecular compounds, the electrons are not transferred, and your book talks about that. But we're going to treat them as though they were transferred. So remember that you're talking about transferring from an atom that's less electronegative to an atom that's more electronegative. And therefore, the patterns that we see for oxidation numbers are really determined by electronegativity. So some rules that you should know and should have memorized. If you have free elements and they're uncombined states, then their oxidation numbers are 0. So anytime you have an element, whether it be diatomic or not diatomic, like P4, but it's all one type of an element, then the oxidation number of every atom in that element is 0. Individually, every atom is 0. They are truly atoms. If you have an ionic compound, so this would be in monatomic ions in ionic compounds, then the oxidation number is equal to whatever the charge is on the ion. The reason it is a monatomic ion is because it completely transferred electrons away from it. So however many electrons it gave away is the oxidation number. Also notice that when we write oxidation numbers, we put the number first. When we write ion charges, when we write oxidation numbers, we put the charge first, and when we write ion charges, we put the number first. This is a very small distinction between the two, but knowing it makes you look very literate, so try to keep that straight. So I gave you some examples here, like lithium 1+ would always be +1 for an oxidation number, or oxide, which is 2-, would be a -2 for an oxidation number. The ones that you know from the periodic table are not always correct if you're talking about in molecular compounds. And so once we get below here now, we're pretty much talking about if it's molecular, you have to make a decision. So oxygen is usually -2, and this is important because it's the ion charge that you would predict, but even when it's in a molecule, it's usually -2. The exception would be like in peroxide, where O2, 2- is the total of 2-, each O is 1-. Hydrogen is almost always 1+, or +1, excuse me. This is what you would predict. So that's because hydrogen is almost always bonded to nonmetals. So it is +1 in most compounds. That would be molecular because it would be bonded to other non-metals, and in that case hydrogen will be the less electronegative, so it will be the +1. But if it's bonded to a metal, then it is more electronegative, and hydrogen will be -1 because the metal will have to be positive. The ones that you know from the periodic table that always are true then would be group 1A and group 2A, and fluorine only would be -1, not the rest of the halogens. And you'll see as we do this, some of our examples, the halogens will have positive oxidation numbers, because if you put a halogen with oxygen or with nitrogen, oxygen or nitrogen are more electronegative, so they'll be the negative, and the other halogen then would be the positive. I know this is a little confusing. To calculate oxidation numbers, you want to pay attention to the fact that if you have a molecule, then the sum of all the oxidation numbers equals the charge on the molecule, and a molecule is neutral, so the sum has to equal 0. And if you have the oxidation numbers that you're trying to find are in an ionic compound or a polyatomic ion, in a polyatomic ion, then they have to equal the sum of the charge of the ion. So in like bicarbonate, like the example that's shown right here, the bicarbonate's charge is -1. That means that the total of this has to equal -1. So if it's in a compound, that would be neutral. It has to equal 0. Sounds confusing. One last exception that's really rare that College Board even talks about it is that you can have oxidation numbers that are not integers, that are fractions. It's rare, and this would be really like more of a combination, like an average. In the superoxide or the superperoxide ion O2 1-, technically what you have happening here is that one atom is neutral and the other atom is gaining an electron. So the average of the two is -1/2. Very unusual, but I don't want you to be afraid if you actually end up calculating half oxidation numbers. It just means that you have to have two atoms to give you one electron, okay, or to take in one electron. So here's an example that is set up for you so that you can write it already if you'd like, and then I'm going to walk you through a few. The bicarbonate ion HCO3 1-, because it has a 1- charge, the sum of all of that has to equal -1. We know from our rules up here that the oxygen is -2 and the hydrogen is +1 because it's not with a metal. So I'm going to set this up algebraically, as in, and it's kind of not in order, but this would be accounting for 3 oxygens, and this would be accounting for 1 hydrogen, and then I have the carbon that I don't know, and the total has to equal -1. So when I set up the algebra, I get a total for the carbon of +4, and there is only 1 carbon there. So the oxidation number of the carbon would be +4. So if I asked you to list them, you're going to list them. Hydrogen equals +1, carbon equals +4, and oxygen equals -2. Notice that we're talking about each oxygen, not the total of all the oxygens. Okay, so let's do a few so that you can practice. You may want to just watch first and then stop and write when you're finished. I'm going to set them up algebraically for the first one, and then maybe the second one, and then after that I'll show you a little bit more of how I really do it so that you can start to learn the shortcut. So when I do this, sodium, this is the iodate, so this is sodium iodate, is a neutral compound. There's no charge on that, so the total has to equal 0. So I'm going to set up 1 sodium and 1 iodine and 3 oxygen, and the total equals 0. I know sodium's charge, so this will be 1 times, or oxidation number, excuse me, times +1. I do not know iodine's oxidation number, so this is going to be 1 times X, or 1 times iodine. And I do know oxygen's oxidation number as -2, so that will be 3 times -2, and the total has to equal 0. So this gives me -6 and +1 plus X, all right? So this is a total of -5 plus X, or X equals +5. And the oxidation number of the iodine in here is equal to +5. And then I would rewrite it also as the sodium as +1 and the oxygen as -2. And this would be how I would write all of those oxidation numbers. Okay, I'm going to do the same thing for the dichromate. Let me change colors so you can tell them apart. I have 2 chromium plus 7 oxygen, and now it has to equal -2 because this is an ion with a charge of -2. So I'm going to set this up as 2 times the chromium, which I don't know. I do know the oxygen, plus 7 times -2 for the oxygen. And sorry, that didn't go. And the total has to equal -2. So mathematically speaking now, I get 2 chromium equals 7 times -2 is -14. Move it to the other side, and I get +12 by combining it with a -2. And then I divide by 2 to get chromium equals +6. And I'm going to list the oxygen as -2 because I knew it. All right. Finally, I'm going to do IF7 the way I would really do this. This all has to add up to 0 because it's a neutral compound. So my brain pictures this as 2 halves. The fluorine would be -1 each, so that gives me a total of -7. That means this has to be a total of +7, and there's only 1 iodine there. So this would be I equals +7, and, oops, sorry, and not O. F equals -1. We'll do a lot more practice of this in class, but I want you to feel pretty confident with it. So think about where your difficulties might be and be ready to ask. Okay, so now we're going to talk about how this works in reactions. So your book makes a really big deal talking about how the electrons are transferred, that the electrons are not just sent into space or taken from nowhere. So you have to have an oxidation that accompanies every reduction. You have to have a loss of electrons to accompany every gain of electrons. And we do this by thinking of them in half reactions. So one would be the oxidation half reaction, and one would be the reduction half reaction. And they accompany each other, they go on at the same time. You should know that oxidation is a loss of electrons, which means that if you're losing electrons, it means that your oxidation number gets more positive. It increases because you're losing electrons and it gets more positive. And if you're reducing, you're gaining electrons, and this means that your oxidation number gets more negative. It may not become negative, but it's going to be more negative than it was. And this is how you want to think about it. So the word reduction comes from this reduction in oxidation number because it's going down on the number line. Oxidation comes from most of our reactions when we first discovered these were a reaction of something with oxygen gas. And so when it lost electrons to the oxygen, and we said it was oxidized because it reacted with oxygen. So that's where those names come from, but you need to be able to tell them apart quickly. So there's a couple mnemonics you can decide. I just always remember that the oxidation number goes down, right? Goes down is a reduction, and that the opposite is the oxidation. No, so that's a way to kind of think of it. Goes up is oxidation, goes down is reduction. Or you can use the mnemonic as oil rig. Oxidation is loss, and reduction is gain. Or you can say Leo the Lion says GR, right? Where you're saying gain electrons is reduction, and Leo, lose electrons is oxidation. So I don't care how you remember it, but you need to remember it so that you can work with it quickly. Finally, I'm just going to show you a couple of examples so that you can see how this works. Mostly the reactions that you're used to seeing that are redox reactions are single replacements, where the two substances come in contact with each other directly, and the reaction occurs on the surface of whatever's happening there. So you can see that in this, the zinc is being forced to turn into zinc 2+ ions, which are coming off and gaining in solution, and the copper 2 is collecting those 2 electrons and becoming solid copper. And this is going to happen on the surface of the zinc because that's where the zinc atoms are free to make zinc ions. If you go backwards, then what you're talking about is what's really occurring. And so you can see that in this case, these are showing you the view from the zinc or the view from the copper being formed. And so this is kind of your way to look at this. Or we can put copper wire down in silver nitrate, and we actually have the copper becoming copper ions and the silver ions from the silver nitrate becoming solid silver. So these are just some examples for you as they gain and lose electrons in conjunction with each other. The other way to look at it would be in the half reactions. And so I'm going to show you this so that you can see how they split apart. You can see that we're going to do net ionic equations. And so because copper sulfate is soluble, technically it is Cu2+ and SO4 2-. And because zinc sulfate is soluble, technically it's Zn2+ and SO4 2-. And the sulfate is a spectator, which means I really have two processes going on here. I have zinc forming zinc 2, and I have copper 2 forming solid copper. So we're going to write those as two separate, what we call half reactions. The zinc forms the zinc 2+, and in order to do that, it has to lose 2 electrons. Notice that this means that its oxidation number is going up, and the electrons are written as products, because technically it's producing 2 electrons. Okay, so this is an oxidation where the electrons are being produced, being given off. If I'm doing the reduction, now I'm going from copper 2+ to solid copper, the oxidation number went from 2+ to 0. And so we have a reduction in oxidation number. The copper 2+ is reduced, and the electrons are written as reactants. And this is because this can't occur if that copper can't take in 2 electrons. So we can kind of see how this would work. You can see another example here below. This would be solid copper, as copper with an oxidation number of 0 forms the nitrate as a spectator, so forms copper with an oxidation number of an ion charge of 2+ or an oxidation number of 2+. And here, this would be 2 silver 1+ or +1 if you're talking about oxidation number, forms 2 solid silver. And we need to see why it takes 2 of those, and that would be because for copper to form copper 2, it has to lose 2 electrons. Both of those 2 electrons have to be transferred. For silver with 1+ charge, to make silver solid, it has to gain only 1 electron from 1+ to 0. Which means that now I have 2 electrons being given off by the copper and only 1 electron being gained by the silver, which means technically I need to multiply this equation by 2 to give me 2 silver ions to accept the 2 electrons and form 2 silver atoms. So we'll talk about this more in class, but I just wanted to kind of expose you to that. Finally, you should be able to recognize now oxidation and reduction. Most of the time, it's 2 separate substances, but every once in a while, a single reactant is both oxidized and reduced. This is called a disproportionation reaction. It's just a term, but it's a term that you probably should be familiar with. And notice that in this case, my chlorine is Cl2. And so really what's happening is I have 2 chlorine atoms stuck together in Cl2. One of them, both of them are atoms. They both have a neutral charge or a neutral oxidation number because they can't fight with each other, so no one wins. And one of them is becoming Cl-, so it's going from 0 to negative, and it's the reduction. And one of them is forming Cl with an oxidation number in chlorate of +5, and so it's going from 0 to +5, and it's giving you an oxidation. So technically, if you were writing this as half reactions, you'd have to leave it as Cl2 because they're together, forming Cl-, and you'd make it Cl2 forming ClO3 1-. And now we'd have to talk about how to fix this, but these would be your 2 half reactions. The Cl2 forming Cl- would gain electrons. I'm not going to talk about the number there. The Cl2 forming Cl5+ would lose electrons, and so we would have a number of electrons as a product. Okay, so think about what you need help with. That should have covered everything. I think that I wanted to add to what you put in your learning targets, and I'll see you soon.